Professor R. Ashokamani, former professor and head of the Department of Physics, Anna University, Chennai, and presently guiding 5 research scholars. He has more than 40 years of UG and PG teaching experience and 25 years of research experience. 14 research scholars have obtained doctorate under his guidance in the area of solid-state physics. He has more than 150 research publications to his credit, of which 90 are in international journals. He has authored a book on solid-state physics which has an international publication. He has participated in several international conferences both in India and abroad. He is a fellow and treasurer of Tamil Nadu Academy of Sciences.
Welcome to the UGC lecture series on applied electronics, and this talk will be from the section on bonding in solids in the paper on physics of materials, which forms a part of the course. And in the section on bondings in solids, we will go through secondary bonding, that forms the lecture number 8, and in the section on secondary bonding, the contents of the lecture are as follows. We will talk about the hydrogen bond, van der Waals bonding, comparison between the primary bonds and secondary bonds, properties of solids with different bondings. As I told you in the last lecture, the secondary bonding primarily arises because of the formation of dipoles, and the dipole interactions occur between induced dipoles. You can have a molecule, every molecule, as you know, should be neutral, but due to thermal agitation there may be induced dipoles, and one induced dipole will have an influence on another dipole which is neutral. So, the neutral molecule will become an induced dipole. So, one induced dipole will act on another dipole which may be neutral and induce a dipole moment. So, you can have dipole interactions occurring between induced dipoles and polar molecules. You know, a polar molecule is one which has got a permanent dipole moment. An induced dipole moment is an instantaneous one, that is mainly occurring because of thermal agitation and asymmetric charge density distribution of the electrons. The electrons are not distributed in a uniform manner, there is asymmetric distribution of electronic charge density, that gives rise to a fluctuating dipole moment. On the other hand, a permanent dipole moment, dipole is one in which the positive center, charge center, negative charge centers are permanently separated. It is called a permanent dipole. So, you have the polar molecules which have got permanent dipoles, and you can have interaction between polar molecules themselves. For instance, water molecule, as all of you know, is a polar molecule. Water molecule is a polar molecule. Supposing you got one water molecule, another water molecule, then there will be dipole-dipole interaction. Now, the dipole-dipole interactions are called the van der Waals bonding, and if you would have studied about van der Waals bonding in the earlier years in the high school you talk of van der Waals bonding, but wherein you say that there is attraction between gas molecules. How can you visualize or understand attraction between gas molecules? After all molecules are neutral. Between one neutral molecule, another neutral molecule, or between the neutral molecules, how can there be attractive interaction? So, the origin of attractive interaction that is present between the molecules of gases. You know the fact that the gases can be liquefied and solidified, almost all gases can be liquefied and solidified, excepting helium cannot be made to go to the solid, right. I do not want to go to the reasons. Helium, you do not have solid helium, but all gases can be liquefied and solidified. The fact that solidification or liquefaction occurs, that shows that there is attraction. Where from does the attraction come? That is a so called van der Waals attractive interaction, but at the time of van der Waals, if you had asked, he would not have given any answer, because it was taken as an assumption. He assumed that should be attractive interaction, but the origin of attractive interaction was not known to van der Waals himself. Only on the basis of quantum mechanics in 1940s we understood the origin of attractive interaction between gases, or the van der Waals attraction, right, the origin of van der Waals forces. Then the hydrogen bonding is a special case of the secondary bonding, about which we are talking about. And the secondary bonding, as I told you in the last lecture, may be due to fluctuating dipoles, wherein there will be instantaneous dipoles being formed. You have a dipole here, another dipole here, wherein the positive and negative charge centers are separated. And the other reason for secondary bonding will be permanent dipoles, between one permanent dipole that you have got here, another permanent dipole. So, permanent dipole interaction, right. So, this is yet another reason for the secondary bonding. And the fluctuating dipole bonds, as I told you, is arising because of thermal motion of the atoms. That is the reason why you have a fluctuating dipole moment, a molecule acquiring a fluctuating dipole moment. It is because of the temperature, right. The electron densities around the nuclei are getting distributed in a asymmetrical manner. That is the reason why the positive and negative charge centers do not coincide, thereby giving rise to a fluctuating or instantaneous dipole moment. So, permanent dipole moments, dipole bonds on the other hand are formed between weak intermolecular bonds are formed between molecules which possess permanent dipoles. A dipole is formed in a molecule if there is asymmetry in its density distribution. Now, let us look at the water molecule. You can have any diffraction method by you can perform X-ray diffraction to understand the structure of water molecule. By now the water molecule consists of two hydrogen atoms. You have two hydrogen atoms here, and you got a water molecule here, right. The angle that separates the two bonds, you got OH bond and OH bond, oxygen and hydrogen, the bond connecting these two atoms, and similarly these two atoms here, the bond angle is 104.45 degrees. That is the geometry of the water molecule, right. You have got two hydrogen atoms and you have got oxygen atom at center, that is H2O, right. And the distance separating that oxygen hydrogen is 0.9584 angstrom unit. Now, as I told you, because of the fact that there is a asymmetric charge density distribution of the electron cloud. Now, how do you understand this? Now, you look at the oxygen atom here, you have got the oxygen here, the oxygen atoms here, the hydrogen is here, and you look at this region, right. Now, you have got oxygen. What do you have? What do you know about the electronic configuration of oxygen? It will be S2P4 requiring 2 electrons so that the octet structure is retained. You know, I told you about the octet rule. Every atom tries to attain the octet structure. When I told you about NaCl and ionic bonding, sodium atom gives an electron to chlorine. Why sodium should give or why chlorine should accept? It is because of the fact that sodium tries to go to the neon structure having 8 electrons outermost shell, and chlorine, by accepting an electron, goes to argon structure. What I would like to tell you is both sodium and chlorine, they try to attain the octet structure. Similarly, in the process where the oxygen trying to attain the octet structure, it shares an electron with hydrogen. The hydrogen atom has got one electron. That electron is shared between oxygen and hydrogen, and similarly this hydrogen also will have one electron that is shared between these two. As a result, the sharing occurs, but here what happens is there will be lot of electron charge cloud, right. The unbalanced electronic cloud will be present here. So, in the diagram, this red region, wherever you got red region is a negative. So, you got negative charge accumulated here, right. The important point is that should be understood is this region will be more negatively charged compared to this region. This is positive, the green region refers to a positive, this is positive because one electron is there with the hydrogen, that is shared by between hydrogen and oxygen, whereas here you got a number of other electrons among the S2P4, more electrons are found in this region. So, this region will be more negatively charged compared to this region and this region. So, there will be asymmetric in the electronic charge density distribution in the case of H2O. So, the approximate shape and charge distribution in water molecule is given by this picture. This shows that there is asymmetry, a high degree of asymmetry that drives the H2O molecule to acquire a dipole moment. What do you mean by dipole? That is, the positive and negative charge centers are separated, right. In an atom, you got a proton and electron, maybe in the hydrogen atom, the two charge centers will be, they will be lying one over the other, the charge centers coincide, whereas in this particular case the charge centers will not coincide. That is the reason why it acquires a dipole moment, and the experimental dipole moment that has been measured for water molecule turns out to be 1.2 debye. Debye is the unit by which the dipole moment is measured. It is expressed in terms of so many debyes. So, the dipole moment of water molecule is 1.8 debye. So, in short, I would like to tell you that a water molecule is a polar molecule. It has got a permanent dipole moment, and the permanent dipole moment occurs because of the fact that the electronic charge density distribution is asymmetrical, right. So, a water molecule is a polar molecule. Okay. Now, as I showed you earlier, the angle that separates the two hydrogen atoms will be around 105 degree or 104.5 degrees, and this region will be positive, whereas this region, as I told you earlier, this is negative, right. This is a negative, that is what I am showing here again. This is a negative side, this is a more charge that is residing here will be negatively charged, and here it is on the positive side. So, intramolecular bonding, the important point is intramolecular bonding H2O is due to covalent bonding. Whether you understand this point, the intramolecular, within the molecule you have got two electrons shared, like hydrogen molecule. What happens? You have got one hydrogen and another hydrogen. H2 is the simplest example for covalent bonding. So, there will be one electron with the hydrogen atom, and oxygen will give one electron here, two electrons will be found here. So, the two electrons which are found will be shared, and two electrons will be found which will be shared here. So, between H and O the bonding is covalent bonding, and here also covalent bonding. the intramolecular bonding is covalent bonding. That should be clearly understood, right. The intramolecular bonding is the covalent bonding. Oxygen and hydrogen are bonded together by sharing electrons, but the oxygen atom pulls the shared electrons closer to it, creating negative and positive sides of the water molecule. So, in the water molecule, if you take a single molecule, there will be a positive region, and the more important thing is this will be negative, right. Therefore, this will be comparatively, this side will be positive. Therefore, there will be a permanent dipole moment, which is associated with each and every water molecule. Each and every water molecule will have a dipole moment, which has been measured to be 1.8 dBi is the dipole moment associated with each and every water molecule. Okay. So, you look at the hydrogen bond. Having understood about water molecule, this is oxygen here, 2 hydrogen atoms here, right. You try to understand hydrogen bond, right. Hydrogen bonding between water molecules, right. You got one water molecule, right. You got oxygen here, 2 hydrogen atoms here, H2O, right. This is another H2O, right. As I told you here, this region remains exposed, in the sense that the electron cloud here, the electron here will be shared between these two, will be shared, the covalent bonding between the hydrogen and oxygen, covalent bonding, that is sharing, right. You do not have hydrogen atoms on this side. So, this region is completely exposed, and so this will be more negative, right. This will be more negative. Now, if another hydrogen atom comes here, then the electron cloud will attract the proton. Already the electron here will be shared between this and this, right. The electron is shared, remember this hydrogen atom will have only one electron, that is shared. The electron cloud will be somewhere here, right. The hydrogen atom which has got one electron will be shared between the oxygen, and the sharing occurs here. And so, in the case of hydrogen molecule, the intramolecular bonding is the covalent bonding. So, we have to understand the force that is operating between water molecules. The H2O molecule, you have got a H2O molecule, the oxygen is here, the 2 hydrogen atoms are here, and the intramolecular bonding is covalent bonding. Now, what is hydrogen bond? The intermolecular bonding is the hydrogen bond. You should remember the intramolecular bonding, the bonding within H2O molecule, water molecule is covalent bonding, right. The bonding that occurs between one water molecule and another water molecule, or between water molecules, right. You have got water here, between water molecules you have got water here, between water molecules the bonding that is present is the so called hydrogen bonding, right. You have got hydrogen bonding here. So, okay, the hydrogen bonding is very important. I will come to that later, why biologically hydrogen bonding is very important. So, electrical attraction between water molecules leads to hydrogen bonding. So, electrical attraction between water molecules leads to hydrogen bonding. By electrical attraction, what I mean is the electrostatic force operating between the positive side of this region and the negative side of this region, the negative and positive, they will attract each other, right, giving rise to what is called the H bond, the hydrogen bond, right. Okay. Let us now look at the case, namely each hydrogen atom in water molecule is covalently bonded. This I want to stress again, the intramolecular bonding is covalent bonding. And now, with respect to oxygen, by shared pair of electrons, you have been studying that in covalent bonded solids, there is sharing of electrons between the two participating atoms, right. Especially in hydrogen molecule, the electrons participating are equally shared, that is sharing. And oxygen also has 2 unshared pairs of electrons, right. And there are 4 pairs of electrons surrounding the oxygen atom, 2 pairs involved in covalent bonds with hydrogen, and 2 unshared pairs on the opposite side of oxygen atom, So, oxygen is an electronegative or electron loving atom compared with hydrogen. What I am trying to tell you is, now there is sharing here, sharing here. Now, there are unshared electrons here, right. The unshared electrons are here, and that is the reason why the molecule becomes a dipole. Okay. So, the polarity of a molecule, you say polarity or the dipole moment that is attributed to a molecule is because of between two species. A molecule means you have got two atoms coming to bonded to each other, or three atoms bonded to each other, NH3 or whatever be the thing, and between the two participating species, the electronegativity difference will be large. You take for instance hydrogen atom, it is electropositive. If you look at the periodic table, hydrogen is on the left side, then oxygen or chlorine, you take HCl, or oxygen hydrogen, right. The O atom or the Cl atom, they are on the right side of the periodic table, they are more electronegative, but the hydrogen is electropositive. So, electronegativity plays a very important role for the molecule to acquire a net dipole moment. So, electronegativity concept is very important, right. So, oxygen is electronegative compared to hydrogen, and that is the reason why hydrogen combined with oxygen becomes a dipole, right. Water is a polar molecule, meaning that there is an uneven distribution of electron density, as I told you. Water has a partial negative charge delta minus near the oxygen atom due to the unshared pairs of electrons, and partial positive charge delta plus near the hydrogen atoms. So, the regions that I have been talking about, you have the I showed you in one of the pictures earlier that you have the delta minus, delta plus and all these things, and so there will be delta plus, right, and this is delta minus. So, okay, that is what I am trying to tell you again, delta minus negative charge and delta plus positive charge near the hydrogen atoms, and an electrostatic attraction between the partial positive charge near the hydrogen atoms and the partial negative charge near the oxygen results in the formation of hydrogen bond as shown in the illustration, right. So, this is what happens here, because the electron associated with the hydrogen atom is getting shared. So, this is more positive, right. That is the reason why you put delta plus, delta positive, here delta minus, right. This region is more negative, this is more positive, resulting in the hydrogen bonding between two water molecules, one water molecule, another water molecule, right. So, let us now go to the animation. Let us see what happens, how the water molecules arrange themselves in a particular fashion, so that liquid water becomes icy, right. You see the formation, I see the structure of the condensation of the molecules into the solid phase. You started with one H2O molecule, right, H here, O here. Now, you should see that the important point is you look at the H atom here, hydrogen atom here, right. This hydrogen atom is seeing the electron cloud of the oxygen, right. There is that gives rise to attraction between the one H2O molecule and another H2O molecule, right. Okay. See again you observe now the H atom, the O atom here, the unshared electrons, the delta minus, the negative region is attracted by the positive region, right. The negative region is attracted by positive region, that is the hydrogen bond, and number of water molecules will come like this, and they give rise to the formation of ice, or the material goes to solid state. Water when condensed will become ice, right. Water when condensed at 0 degree centigrade it will become ice. So, the formation of ice is because of that. These bonds can occur between molecules intramolecularly or within the different parts of a single molecule, either intermolecularly or intramolecularly. The hydrogen bond is stronger than that of the van der Waals interaction, which we will be discussing later, but weaker than covalent or ionic bonds, right. Hydrogen bond, remember, is stronger than the van der Waals bond, right. I will come to van der Waals bond little later. This type of bond occurs in both inorganic molecules such as water and organic molecules such as DNA. So, DNA, which is biologically important molecule in DNA, and the type of hydrogen bond occurs in DNA, and so that gives the enormous importance associated with the hydrogen bond, right, which is the strength of the hydrogen bond is much greater than the so called van der Waals bond. The term hydrogen bond is arising because of the fact a hydrogen bond is the attractive interaction of a hydrogen atom with an electronegative atom such as nitrogen, oxygen, fluorine. You can have H N or oxygen H2O, right, hydrogen fluoride, that comes from another molecule or chemical group. Therefore, you can have HCl, right, hydrogen. So, one will be electronegative, and hydrogen, remember, it is electropositive, it is in the periodic table on the left side. The other atoms, you know, oxygen, nitrogen, fluorine. Fluorine is a superhalogen, right. You know, fluorine in the Pauling scale, the value of electronegativity is 4.0. It is a super halogen, it is a highly electronegative. The most electronegative element in the periodic table is fluorine. Okay. So, hydrogen fluoride is highly ionic, right, highly ionic, and therefore, hydrogen bond is attractive interaction of a hydrogen atom. So, hydrogen will be present, the another atom. So, electronegativity plays a very important role. The electronegativity difference gives the magnitude of the dipole moment, or the polarity arises because the electronegative difference between the hydrogen atom and the other atom, which gives rise to hydrogen bond, right. The hydrogen must be covalently bonded with to another electronegative atom to create the bond, right. And let us now pass on to the van der Waals bonding. It arises due to dipole-dipole interaction. Having completed hydrogen bonding, we have gone to the van der Waals bonding. The van der Waals bonding arises due to dipole-dipole interaction, right. The origin of dipole moment is a thing that should be understood. Origin of dipole moments in neutral helium, neon, argon, krypton, xenon, they are the inert gases, right. How can you expect a inert gas atom to acquire a dipole moment? That is beautiful thing will be, it is a symmetrical atom, you know, they where from you are getting the octet rule, neon, argon, krypton, xenon, the rare gas elements, right, the last group in the periodic table, the inert gas structures, they have the 8 electrons outermost shell, they are spherically symmetric, the electronic cloud will be spherically symmetric. Then how does these atoms get electrical dipoles? How do they become dipoles? It is only from quantum mechanics the atom or a molecule acquiring dipole moment could be understood. The important point is only quantum mechanics can explain as to how these atoms which I am mentioning here, helium, neon, argon, krypton, xenon, radon, now these things acquiring a electric moment can be understood only on the basis of quantum mechanics. The potential that comes into operation is the famous Lennard-Jones potential. So, I will talk to you about Lennard-Jones potential to a greater extent, which is which has been used quite extensively to understand the properties of gases in general and also very many other cases, right. So, the Lennard-Jones potential will be having this following form: U of r is here, right. The potential energy experienced by an atom which is kept here, when another atom is coming from here, this is the potential energy profile. This from the very first lecture I have been telling you about the cohesive energy curves. The cohesive energy curves will have this following form. There is a positive region, there is 0 here, there is a positive region, there is a negative region. This gives them the potential energy experienced by a particular atom because of another atom. You have got the origin here, another atom is coming from here. What is the potential energy that is experienced by this atom, or in other words by this atom from the neighboring atom. So, assume that you have got one atom at the origin, another atom is coming from infinite distance. At infinity the potential energy will be 0, right. The energy exerted by an atom which is kept here on this will be 0, right. So, when the atom moves, the attractive part, the attraction increases and so on, it reaches a minimum. In any potential energy profile, the potential energy drawn as a function of distance, the minimum gives them the stability, and this is called the cohesive energy. In the very first lecture I mentioned to you the meaning of cohesive energy, and in all bondings the shape of the curve will be similar as to what I am showing here. And let us now pass on to the summary session. The secondary bonding arises due to attractive interaction produced between fluctuating dipoles, or the interaction occurring between fluctuating dipoles and permanent dipoles, or between permanent dipoles, as in the case of van der Waals interaction, that is attraction occurring between the permanent dipoles, right, permanent dipoles. Whereas, in the other cases it is generally called a secondary bonding. The last one is called the van der Waals interaction, wherein the bonding occurs between permanent dipoles. Hydrogen bonding is a special case of secondary bonding. The van der Waals bonding can be explained only on the basis of quantum mechanics. Not only that, in all bondings, whether it is primary bonding, secondary bonding, the quantum mechanics plays a very important role, because of the fact that the electrons are responsible for bonding, all bondings, metallic bonding, ionic bonding, covalent bonding. Okay. In all bondings the electrons are coming into operation. Therefore, electrons are not classical particles, they have to obey the quantum mechanical rules. So, quantum mechanics plays a very important role. Without that you cannot explain any of the bonding. Now, we will pass on to the question session. Question number 1, what is hydrogen bonding? Question number 2, why hydrogen bonding is so very important? Question number 3, what is van der Waals bonding? Question number 4, whether hydrogen bonding is stronger than the van der Waals bonding. With this we close this lecture. We will resume with the rest of the material in the lectures to come. Thank you.